to Educator.com. Today we're going to talk about polynomial functions, starting with some review and then going on to discuss the topic of analyzing the graphs of polynomial functions. Okay, a polynomial in one variable is what we're going to start out with, and a polynomial of the degree n in one variable x is an expression in this following form. A to the n, the leading coefficient, cannot be 0, because if it was to be 0, this would drop out and then you'd actually have a lower degree polynomial. And n is a non-negative number, so we're not going to have a negative coefficient up here. This first coefficient is called the leading coefficient. A polynomial is just an expression in which the terms are monomials, and a restriction on this is that there cannot be variables in the denominator. If there were it would not be in this form if that were the case. You'd have something else. You'd have a rational expression, not a polynomial. Now, let's talk about degree using numbers instead of just n. If you have something such as 3x to the fourth, a polynomial, plus x cubed minus 4x squared minus x plus 4. Okay. The degree of the polynomial is the degree of the variable that is the highest power. So right here, the highest power I have is 4. So therefore, the degree equals 4. And the leading coefficient is the coefficient for the variable that is raised to the highest power. One thing to be aware of is that you might look at a polynomial and it could be written like this. 2x squared minus 6x to the fifth plus 4x cubed plus 9. And when you look at this, you've got to realize that these are not written in descending order. So you can't just look at the first one and say, oh, this is degree 2. Before you figure out what the degree of a polynomial is or what the leading coefficient is, you first need to write it in descending order. So that'd be negative 6x to the fifth plus 4x cubed plus 2x squared plus 9. Here, the degree is actually 5, and the leading coefficient is negative 6. So just make sure that the terms are in descending order before you determine the degree and the leading coefficient. Now, polynomial functions. So we just saw this form, but now we're talking about it as a function. A polynomial function of degree n is a function in this form. You may see this written as f of x like this. You may also see p of x is sometimes used for a polynomial function. And just to give you an example, I'm going to call it f of x, but it could have been called p of x equals 2x cubed minus 4x squared plus 8x minus 5. So this is a polynomial function. And with polynomial functions, we can evaluate the function for both numerical values and algebraic expressions. So you're probably familiar with evaluating functions for numerical values, but evaluating them for algebraic expressions may be something new. So first, just looking at a function, f of x equals 4x cubed minus 3x squared plus x minus 1. And if I'm asked to find f of 2, the strategy is just going to be to replace all of these x's with 2's. Which is going to give me 2 times 2 is 4, times 2 is 8, so it's 4 times 8, 2 to the third is 8, minus 3 times 2 is 6, plus 2 minus 1. So this is 32 minus, actually, correction, this is x replaced with 2. 2 times 2 is 4, because that is squared, so it's going to give me 3 times 4. So I'm going to end up with 4 times 8 minus 3 times 4 plus 2 minus 1. So this is going to give me 32 minus 12 plus 2 minus 1. Simplifying that, 32 minus 12 is 20, plus 2 is 22, minus 1, that's 21. So f of 2 is 21. That's straightforward, but something you may be less familiar with is the idea of something like this. F of 8 plus 3. Again, I'm going to substitute this expression for the x's. Same idea, only now I've got a variable in here. So wherever there's an x, I'm going to put in 8 plus 3 instead. Now, you could do the algebra and work this out to figure out the value, but the important part is just knowing how to set this up by substituting this algebraic expression for the variable in the function. Okay, a point at which the graph of a function intersects with the x-axis is called a zero of the function. And previously, we've referred to x-intercepts. This is the same thing, only different term. And the degree of the function can tell you something about the zeros. If a polynomial function has an odd degree, there is at least one zero. For example, if I have something like f of x equals 6x cubed minus 5x squared plus 8x, the degree here is 3, and it's odd. So I know that it has at least one zero. Now, just showing you examples of zeros, polynomial functions, so we talked about linear functions, which graph is a line, and then quadratic functions, which are polynomial functions, are parabolas. You can also have more elaborate shapes, such as this, with a polynomial. And everywhere that intersects with the x-axis, those are all zeros. So this actually has 1, 2, 3, 4, 5 zeros. And if, let's say this is 2, 4, 6, 8, 10, negative 2, negative 4, negative 6, negative 8, negative 10, you could find the values for these. So, for example, one of the zeros is at 4. So you could find the values for these zeros. Okay, so you always have at least one zero if the degree of the polynomial function is odd. If the degree is even, it may or may not have a zero. It may or may not intersect with the x-axis. So something like this might have a zero, might not. So the degree equals 4. It's even. It may or may not have a zero. Thinking back to quadratic equations, which their degree is 2, something like x squared plus 2x minus 1, quadratic functions, recall that these parabolas sometimes have a zero. They sometimes intersect with the x-axis. They can have 1 or 2 zeros. This one is 2. Or they may not intersect. We saw situations where parabolas did not intersect, and those have even degrees. And the same is true of a polynomial function with a greater degree that is even. Okay, when we talk about functions, we sometimes talk about end behavior. And the end behavior of a function refers to what the graph does as x gets very large or very small. So instead of in the middle, which is often what we've been focusing on with graphing, now we're thinking about the ends. Way out here when x is very positive, way out here when x is very negative. And you can predict some of this end behavior by looking at the degree of the polynomial function and the sign of its leading coefficient. So let's break this down into first talking about even degrees. Okay, and then we'll talk about odd degrees. Polynomials of even degrees first. For example, x plus 4 minus 2x cubed, f of x, plus x minus 8. Okay, so this has a degree of 4. It's even. We can divide this into two categories. Those that have a leading coefficient that is positive. So if the leading coefficient, a of n, is greater than 0, both ends of the graph go upward. Now let's think about what that means. For example, if I have some polynomial function and it's even, so it may or may not have a 0, but I'm going to show it as having 0. Both ends are up. So this is even, and this is a to the n is greater than 0. Both of these ends go up. What this is saying is that when x is very large over here, or x is very small way out here, y or f of x, let's say f of x, is large. So end behavior, what's happening way out here at the extremes when x is very large or when x is very small, we see that y is going to go up, up, up and be very large. So that is an even degree, both ends are up, and it's a positive leading coefficient. So both ends are up, very large y's or very large function values at the extreme values of x. Now, the other possibility, so that's one possibility for even. The other possibility is that the leading coefficient is less than 0. So I have a negative leading coefficient. So something like negative 4x squared plus 3x minus 1. And this is actually a quadratic function. And if you recall, this is going to be a parabola that faces downward. So let's look at this. Here, and this could have had a higher degree, higher even degree, like 4 or 6 or 8. But let's just look at the parabola. Here, both ends face downward. And what this tells me is that when x is large or when x is small or very large, f of x is small, has small values. So at the ends here, when x is these smaller values or very large values, y is going to have a very small value. Okay, so these are even degrees, and to help you remember this, just think back to quadratic equations, because we already talked about quadratic functions and the fact that if their leading coefficient is positive, they face upward. If their leading coefficient is negative, they face downward. And it's the same idea here, except you might have more ups and downs in between. Now, if you have a polynomial with an odd degree, again, we have two possibilities. If I have a polynomial that has an odd degree and the leading coefficient is positive, a is greater than 0, then what I'm going to have is a graph that's going to go up to the right. Graph goes up to the right. So that's this case right here. What this is saying is that when x is large, y is large. Or f of x is large, either way you want to say it. And when x is small, y gets very small. So I just think of it as, okay, x and y are going in the same directions. Now, if the leading coefficient is negative, you have the opposite situation. Here, you'd have something like this, where, so this is odd degree, and it is a of n is negative. Here, I see that it's starting up here and it's going down to the right. Graph goes down to the right. So with even degrees, both ends face up or both ends face down. With odd degrees, one end goes up, the other goes down. If it's a positive leading coefficient, it goes up to the right. If it's a negative leading coefficient, it goes down to the right. And you also saw that with linear equations, going up or down to the right. So what this tells me is that when x is very large, y is very small. And when x is very small, y is very large. X and y are going the opposite ways. Okay, first, looking at this polynomial, what is the degree and leading coefficient? I'm going to start out by putting this in descending order. So this is my largest degree here, so I'm going to put that first. Then I have x to the third. I have negative 7x to the second, 3x, and finally the constant. Okay, so now that I have this in descending order, I can easily see that the degree equals 4, and the leading coefficient is going to be the coefficient for that variable raised to the largest power. So the leading coefficient is negative 12. And if I didn't put these in the right order and just looked at it, I might have said, oh, the leading coefficient is 3. So always put the polynomial in descending order first. Okay, given this function, find f of 3a to the fourth. So this is an algebraic term, and we need to find the function value for it. So I'm going to substitute 3a to the fourth everywhere there's an x. I'm going to use my rule here of raising a power to a power that tells me that when I raise a power to a power, I need to multiply the exponents. So first, I've got my 3 here. Let's keep that out here. And I've got to remember to raise 3 to 3 also. So this is 3 times 3 is 9, times 3 is 27. So it's 27. A, and this is 4 times 3, so that's a to the 12th power. Okay, and then here I have 3 squared, which is 9, a to the fourth. Okay, that's 4 times 2, which is 8. And then this just stays as it is. Okay, so next I have 3 times 27, which is actually 81, a to the 12th. Negative 2 times 9 gives me negative 18, a to the 8th. Plus 3a to the fourth minus 7. Okay, and I always double check and make sure I can't do any further simplification, and I don't have any like terms that I can combine. So again, evaluating a function for an algebraic expression just involves substituting that expression in for the variables. Okay. Again, evaluating this function for an algebraic expression means I'm going to substitute in 3b minus 2 wherever I see an x. So writing this out, this is a squared binomial. Okay, so using the FOIL method, first is 3b squared. 3b times 3b is 9b squared. The outer term, that gives me negative 6b. The inner terms multiplied, negative 6b. And the last terms, negative 2 times negative 2 is 4. Now, using the distributive property and multiplying each term within the parentheses by 2 is going to give me 2 times 9b squared is 18b squared. 2 times negative 6b is negative 12b. And this is negative 12b. I also could have just added these first and then done the distributive property. It's going to come out the same either way. 2 times 4 is 8. Now, distributive property again here. Negative 3 times 3b is going to give me negative 9b. Negative 3 times negative 2 is going to give me plus 6, and then a 9. Adding like terms, negative 12b and negative 12b is negative 24b. And I've also got some more simplifying I can do out here. So this is 18b squared. Negative 24b and negative 9b is going to give me negative 33b. 8 and 6 plus 9, so that's 15 plus 8 is 23. Okay, so evaluating this function for 3b minus 2 gives this result. Simply substituting in 3b minus 2 for all the x's, using the distributive property, and then simplifying by adding like terms. Okay, In example 4, we're given this polynomial function and asked to describe the end behavior. So starting out by looking and making sure that this is written in descending order, which it is, because I need to find the degree and the leading coefficient. The degree is 6. So I know that this is an even number, so it may or may not have zeros, just as an aside. Now, talking about leading the leading coefficient and the degree in a little more detail. The degree being even tells me that both ends will be up or both ends will be down. Okay? So I know that both ends are going to go in the same direction with this polynomial. The leading coefficient here is 5, and that's positive. So since it's positive, both ends of the graph go upward. Just like with a parabola with a positive leading coefficient with quadratic functions. So this is to the 6, so it's going to be more complex, but just schematically, the idea is that, and it may or may not have zeros, the idea is that both ends will face up. Now, what does that tell me about the end behavior? What this tells me about end behavior is that when x is large, way out here, y is large, or the function is large. When x is very small, way out here, has small values, y is large. So at the ends, at both ends, x very large or x very small, the function has large values. And that tells me about the end behavior. And I was able to figure that out by realizing this is an even degree, and it is a positive leading coefficient. Okay, that concludes this lesson of educator.com on graphing and polynomials.